Hey kids, time for some more series. I hope you go, if you have a hard hat and any tools, you need to go get them because today we are going to learn how to just grind it out and build our own series. So some of you maybe have any experience with baking or whatever, the notion of, hey, making a cake from a box or making a cake from scratch. So we are going to make some series from scratch, no recognition of anything that knowledge from before, but then we are going to try to find out all the different ways we can avoid making a cake from scratch. Because after all, that's a lot more work. And if I just had a box and I just had to add the eggs and the oil and mix it up and pop it in the oven, that's a lot easier. So that's the big idea of where we're going. So remember, we have a function f of x so far. Again, call it whatever you want. And we have a function that is actually equal to the infinite polynomial, right? Infinite polynomial on an interval of convergence, right? And the interval of convergence is, right, a to b, where the center, what we call the center of the series, is in between a and b. The interval of convergence is a big deal and is very hard, actually, not very hard. It is difficult or long to find the interval of convergence unless you have a geometric series. Then it's very easy. All right, so I'll talk more about that. But then we have what if we have a function that we can represent with a finite polynomial? Right? Infinite polynomial is awesome, but I can't graph an infinite polynomial. I can't plug in values to an infinite polynomial. AP rarely gets upset about the whole equality versus approximate, except here. If you are talking about series, the function is exactly equal to only the infinite polynomial, otherwise is approximated if you cut that polynomial off or make it finite. Okay? This approximation gets better as the number of terms goes to infinity. And of course, if you actually do go to infinity, you have the infinite polynomial, an infinite amount of terms, and then you are exactly equal to the given function. Remember the center, we kind of sort of think of the point of tangency. So far, what we have, all we've been dealing with are infinite series that are of the form geometric. And the geometric series that we have had have all been of the form where x hides the place for what that common ratio is. That's technically x minus 0. Maybe you have x minus 2. So this infinite polynomial, because this is geometric, the numbers that you can use to create convergence, which is what we want, from the center 0 is exactly equal to, because I have a geometric series, gosh darn it, I thought I changed that, is exactly equal to the infinite polynomial, and where you expand this, where n is 0, n is 1, n is 2, which, because this is geometric, is a, or the first term, 1 over 1 minus r, where my r is x, right? My common ratio is covered up by this variable x. So the rational function 1 minus 1 over x which looks something like this, on the interval -1 to 1, open interval -1 to 1, the truncated polynomial, when I don't go to infinity, when I stop at, right? No, I guess I need to make this n, right? So when I stop at n equals 2 or n equals 3, then I approximate 1 over 1 minus x on this interval. I radiate out from the center, and maybe if I use a quadratic, if I stop after n is equal to 2, I have a quadratic that maybe looks like that. And as you can see, it's right as it's not -1 to 1. You can see the purple and the yellow diverge, right, away from one another. Even though I'm supposed to converge on the interval -1 to 1, I'm only going to converge if I have the infinite polynomial. But if I stopped where n is equal to 2, if I went from n is equal to 0 to n is equal to 2 of x to the n, that's not infinite. That is finite. You stop at x to the 0, x to the 1, x squared. That is not equal to 1 over 1 minus x on the interval -1 to 1. This function, this infinite series is exactly equal to 1 over 1 minus r but has an interval of convergence. Because this is geometric, r has to be less than -1, greater than -1 or less than 1. Well, what does that mean? That means x has to be greater than 1, but less than 3. Guess who's in the middle there? 2, your center. If you put 2 in for x, 2 minus 2 is 0, 1 minus 0 is 1, 1 divided by 1 is 1. So you're up here at 1, and let's say, I don't know what this looks like. I guess I could look at it, but between 1 and 3, let's say 1 over 1 minus parentheses x minus 2 looks like that. If you stopped after n is equal to 2, once again, you would have a approximator, and your approximator would radiate out from the center and would be something like this. And again, the cloud, you would not match from 1 to 3, but at the center you would be equal. And then as you would move away from it, if you stopped with n is equal to 2, you're only going to be able to approximate really, a lot closer to 2 than from 1 to 3, right? So that's the big idea of what we're doing. So with series so far, but notice that the only kind of series I've dealt with is geometric. So if you recognize a geometric series pattern, here's my r. This is x to the n with a 6 out front, right? Do you see that? There's my r. So ar to the first, ar to the second, right? Ar to the 0. I said first, I meant 0. Ar to the 0 plus ar to the first plus ar squared plus ar, right? On and on and on and on. This is geometric, right? Of the geometric form, because I can get this series by x to the n and then multiply it by 6, right? There is an infinite. So look, see my equal sign? My equal sign is there because this is an infinite polynomial. 6 over 1 minus x is approximately 6 plus 6x, the tangent line, or approximately 6x squared plus 6x plus 6, which is the quadratic approximator. But notice as soon as I truncate or stop the infinite polynomial and make it finite, I have to change to an approximation sign. This center is still 0. It's just that when you put in 0, you get 6. Because this is geometric, x has to be between -1 and 1. Maybe it looks something like that. And I don't know, maybe it looks completely different. I don't know, I'm just making that pattern up. And this quadratic is close. The cubic would be even closer for a little bit longer from the center, right? The cubic would look like that. Approximately 6 over 1 minus x on the interval of convergence. Says nothing about what these two functions look like, the infinite or the truncated polynomial compared to 6 over 1 minus x. You are only looking at the interval of convergence. And the only reason I know the interval of convergence, again, is because I recognized a geometric pattern. We are going to go into making other series that are not geometric with a formula, and we will not know the interval of convergence yet. It'll take a couple of lessons before we get there. All right, so let's go on. This is what we've done really so far. So here is any power series, but any power series has to be in one of these forms where you have a coefficient times x to the 0, right? Some variable. Right? A coefficient, which is a constant, times a variable to the right. So your powers have to increase as you go along. Old news. Or it has to be of this form where your center has been shifted away from 0. But notice that the constants are still here and your powers start at 0 and increase and keep going forever. Coefficients are constants. The center is also a number like 3, -2, 0. Right? So this center is at 0 because there's no shift on x. This is a shift. Your center is at A. Right? So really, this is the only formula you need to remember, because if A is 0, well, then it naturally is this one, right? This is the form of your power series. We're going to give these names. I am going to call a series whose center is at 0 a Maclaurin series. And I am going to call any series of this form a Taylor series. So Taylor is your bigger set. Taylor is like your rectangle, and Maclaurin is like your square, right? Every Maclaurin series is a Taylor series, but every Taylor series is not a Maclaurin series. Maclaurins have to have a center at 0. Taylor has a center anywhere, so it could be 0. Now, how do I build from scratch? Right? So I'm baking a cake from scratch, not from a box. Or I am building a shed out in the back without it being a kit, right? I'm just buying the 2x4s and doing everything myself. How to construct a power series that isn't geometric. So you start with, I'm gonna do it with McLaurin with the center at 0, just because it's gonna make my math a little bit easier to follow. So I can certainly write x to the 0, x to the first, x squared, x to the third, but how do I get the coefficients? That's the issue. I know how to get the coefficients if it's geometric. If it's geometric, it's a r to the first, right? This is your, right, that value of a in your geometric, not a that goes with the center. So what if I just asked you to plug in 0, the center? Plug 0 into here. What is p of 0? Well, remember, x to the 0 is really a 1, right? But 0, right? This is going to be x to the first, plug in 0, x squared, right? Do you see how all these terms are going to go away? And I just get c sub 0 times x to the 0, which is just a 1. Now think about the derivative. Think about your derivative rules with polynomials. What happens to this number? It's a number. What's the derivative of a number? 0. This is going to go away when you take the derivative. P prime of x is going to be 0 plus what? Bring the 1 down, x to the 0 plus 2 x to the first, blah, 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 right? I guess I could have written that there. Oh, I did. I typed it out. Do you see what happened there? Now plug in the center. When you plug in the center, what do you get? Let's lather, rinse, and repeat. What's the second derivative? Notice what happens. By, right? That goes away. Bring the 1 down, you have an x to the 0. Bring the 2 down, you have an x to the first, so on and so forth. What's going to happen when you plug in the center? And again. All right, let's see if we can identify a pattern from this. Remember, this is what I'm after. I want to know, right, the coefficients. Annoying, this is multiplied by a 2. Annoying, this is multiplied by a 6. It's okay. I can get rid of that nonsense. So here's me cleaning out, right? Cleaning all the rest of that work. Just remember what p sub 0, plugging in the center. Remember, there's no shift. Therefore, center is 0. This is a Maclaurin series. I got the first coefficient by plugging the center into the polynomial. The polynomial at the center is exactly equal to the function at the center, the point of tangency. Look at this though. The first coefficient I got by plugging in the center to the first derivative. The slope of the polynomial is equal to the slope of the function at the center. Now you're probably wondering why I divided that by 1. Remember, my goal was to try to find a pattern. I don't want 2 times the second coefficient. I just want the second coefficient. So I divided, right? I took this p prime of 0 is equal to 2, right? I just divided both sides by 2, right? So I divided by, oh, wait, that's not divided by 2. That's divided by 2. Oh, wait, couldn't I say that's divided by 1? And hey, couldn't I say this is divided by 0? Why would I want to do that? Well, because the third coefficient, divide both sides by 6, but 6 is actually 3! What the hee-haw? There's my formula for how to build a power series centered at 0 for any freaking series. Any series. Notice it has to be differentiable. And to be differentiable, it has to be continuous, right? Continuity is a big deal. So the infinite polynomial, any series can be built with the center, right? The center is plugged into the polynomial and to every derivative. So you have to be able to find the derivatives. And then every term is divided by the same factorial that goes with the power. And the power goes from 0, 1, 2, 3, OMG. OMG. This is a Maclaurin series. Colin is his first name. He was a Scotsman. I'm sure he has a quilt on. Quilt. Ha! Kilt. His wig is terrible. But, what can we say? Somebody probably told him he looked great. Colin Maclaurin. A Maclaurin series. This is the formula for a Maclaurin series, which is the formula to construct terms of a power series regardless of whether you're geometric or not. Regardless. I know that sounds kind of weird. So what I'm going to do, oh, wait, by the way, mx plus b, right? The first two terms of the infinite polynomial are the slope, right? Or the first derivative times x to the first, but it's the linearization of the function at the center, whatever function I'm talking about that I want to make a power series to represent, right? For right now, we have like 1 over, right, or 6 over 1 minus x. There's a function. I want its power series representation. It's geometric. I recognize it. AR to the 0, AR to the 1, AR to the 0. Here's the tangent line, but I should be able to do this with any function. This is the quadraticization, right? That's a word I made up. If you truncate whatever function, the polynomial is always equal to this, but it approximates f of x. So let's practice. I can make any power series if you give me a function. So given f of x, make a power series. And they will always tell you how many terms. AP or on our test, we will always say write out first 4 terms or something like that. Now, I hope you never use, as much as I love Maclaurin, I hope you never use the Maclaurin formula for something that's geometric. This is geometric. I already know what the terms look like. 6x to the 0 plus 6x to the first plus 6x to the second, ... But I'm going to pretend I don't know that. And because I see that x has no shift on it, I'm going to make a power series representation, pretending I didn't recognize it was geometric. 1, 2, 3, 4, 5. So they asked me for the first 5 terms. So step 1. Here's your function. Find its derivatives. If they want 5 terms, I need the original. This is for the original, and these all go with the derivatives. First derivative, second derivative, third derivative, fourth derivative, because this is the original. So there's the original f of x. First derivative, second derivative, third and fourth. Okay, now I do need to find these derivatives fairly quickly, remember? That's step 1. Step 2 is evaluate the function and all of the derivatives you found at the center. Well, hello, if this is a Maclaurin, your center is 0. So you are going to plug in 0 here, 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 and here. That's not the coefficients, though. Remember, to find coefficients, you need to take the appropriate derivative and divide it. What do you divide it by? Factorials, baby. So you're going to plug in 0 here, and you're going to get 6 over 1 minus 0, which is 6. But that is not the coefficient, right? What is this? 6 over, well, this is also 6. What is this, though? Plug in 0. What do you get? What is this? What is this? Right? Every time you're plugging in 0 for x. Those are not the coefficients. You have to divide all of those by the apropro factorial. Match the exponent. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 4 times 3 is 12. 24, right? That's how you get the coefficients. 6 divided by 1 is 6. 6 divided by 1 factorial is 6. 12 divided by 2 factorial is 6. 36 divided by 3 factorial is 6. Guess what 144 divided by 4 factorial is? Yep. Which we already knew. Right? So you do the apropro, you do the original. 0 goes with the actual function at the point of tangency. Then you do the appropriate derivatives, 1, 2, 3, and 4 at the center, and then divide by the apropro factorial. For this, each time I got a 6, which I knew because this was geometric. A Maclaurin series is a power series generated with this formula and centered at 0. Somebody has to give you a function, say, then ask for a power series, and then ask for how many terms. They also have to give you a center unless they use the word Maclaurin. If they say make a Maclaurin, they don't have to give you the center, because what do you know the center is? 0. Oh, don't forget the interval of convergence. This polynomial is exactly equal to 6 over 1 minus x on the interval -1 to 1, because it really was geometric. Where r is, right? That's where the interval of convergence came from. The truncated polynomial is approximately equal to however many finite terms, right? So maybe 6 plus 6x. This function is approximately equal to its tangent line, right? Now, what if I wanted to make a Taylor series? So let's pretend I had the same, but I didn't give you this function, but I gave you kind of the same form, so it's still geometric. Good old Brooke is his first name. He's English. Of course he is, because his first name is Brooke. He's got a little bit better wig, I guess, maybe. I don't know. But let's pretend that my center was -2. Then my function really wouldn't look like 6 over 1 minus x anymore. It would look like that. Right? So I have x1 minus x minus -2, which is where I get the plus from. So I would have to then find all the derivatives using this, which I could do. It'd just be kind of annoying. I'd have to find all the derivatives, and then you wouldn't plug in 0. What would you plug in? You would have to use Brooks' formula, and you would evaluate the function at -2, and you would have x minus -2 to the 0, which of course would be x plus 2. Everywhere you saw an a, you would plug in -2, and then you would divide by the appropriate factorial to get the coefficient. Right? Now, again, remember, technically, this has a 0 to the right under here. 0, 1, 2, 3, 4, yada, yada, yada. Derivatives 4, 3, 2, 1, 0. But you plugging in the center, also the interval of convergence would no longer be, right? This is still geometric, where shockingly, -2 is in the middle. O shift. Now, again, that would be pretty annoying though, right? Thanks, Brooke. But finding all the derivatives of this, again, I could do it. Annoying though. I would prefer not to build from scratch or bake from scratch. If you recognize geometric, please use the geometric series formula. All right, so I hope you actually never do use Brooke or Maclaurin on the 6/1 minus x or the 6/1 minus shift. But what about sine? What if the function I give you is sine and I want a power series representation of sine x centered at 0. Or I could say, give me the Maclaurin power series representation for this, right? I could say either one. If I say Maclaurin, I don't have to say the center. If I say Taylor, I have to say the center even if it's 0. Does that make sense? I hope so. All right, what's step 1? The polynomial, the infinite polynomial, is exactly equal to f of x, which is sine x. How do I find? I know what the power series centered at 0 looks like. X to the 0, x to the first, x squared, x cubed, x to the fourth. But I have to find the derivative. Step 1, here's the original, find the derivative. They asked me for the original, and right, so 1, 2, 3, 4, 5 terms. So I need to find the fourth derivative. And what do I plug into the derivatives and the original? 0, right? So sine x is exactly equal to the infinite polynomial, sine at 0 times x to the first, cosine of 0 times x to the first divided by 1 factorial, right? So you're going to plug 0 in here. Fortunately, you know trig pretty well. The sine of 0 is equal to 0, isn't it? The cosine of 0 is 1. Negative 0 is still 0. Negative cosine of 0 is -1. I'm sorry, -1. And then this is also 0. You like when derivatives are zeros because that's going to knock out some terms now, ain't it? That's not these are not the actual coefficients though. You have to take every derivative and original and divide it by the appropriate factorial. I already put that there. I wish I hadn't. But notice by. So sine x is exactly equal to the infinite polynomial that actually starts at 0. So I don't think I'm going to write that down. And all those even powers dropped out because I had a derivative of, right, sine that went with the second derivative had a sine, the fourth derivative had a sine, and my center was 0, so bye-bye. And this goes on and on forever. Hold the phone. Hold the phone here. My function was sine of x. The center was at 0, so I did all this evaluation, which means, again, I got these terms, the squared term and the fourth term, and therefore the sixth and whatever is all going to drop out, right? So is the first term. Wait a second. Do you remember something about the graph of sine? What did we say the graph of sine was? The graph of sine x was what kind of function? It's odd, baby. It was odd. Look at the look at these are odd numbers. Oh my gosh. What? Mind blown. Mind blown, right? No, it's not a coincidence. Oh my Lanta. The polynomial representation for sine is a freaking odd degree polynomial, right? Where all these terms, and don't forget the sine alternates. Where do you think your freaking calculator comes up with sine of whatever? Remember, you can't, sine of x is exactly equal to that polynomial, but you know what sine of x is approximately equal to? X to the first over 1 factorial minus x cubed over 6 plus x to the fifth over, what is that, 120, 5 factorial? What's the center again? 0. So how about you approximate sine of a number really close to 0 with its polynomial? Like maybe 0.1. Sine of 0.1 then is 0.1 minus 0.1 cubed plus 0.1 to the fifth divided by the apropos factorials plus minus plus. Just for a second, just humor me. Humor me. Firstly, make sure you're in radian mode and hit on your calculator, hit sine of 0.1. Look at that decimal. Look at it. Now, I want you to hit on your calculator 0.1 plus 0.1 cubed divided by 6 plus 0.1 to the fifth divided by 120. Enter. That's, whoops, I'm sorry, I forgot the minuses. I was close, but not that, right? So the middle term is negative. Enter. OMG, freaking look at that, right? What do you think your calculator is programmed with? How it does it? What is it thinking about what and computing what sine of 0.1 is? I don't think so, hun. I think it's got polynomial approximations in it. Whoa, that is crazy. Right? Given f of x is equal to sine x, evaluate sine of 0.1 without a calculator. Well, you can't really evaluate it, but you can get approximator by truncating the infinite polynomial. Cut it off after a couple of terms. Whoa. All right. Oh, wait, before I do that, I wanted to say, what do you think would happen if I asked you to construct a Maclaurin power series for cosine of x? You're going to follow this same phenomenon. My function is cosine of x. It's a Maclaurin, so you're going to have center still at 0. Your first derivative is negative sine x. Your second derivative is negative cosine x. Your third derivative is sine x. Your fourth derivative is cosine x. Plug in right? What is cosine of 0? 1. What is negative sine at 0? 0. What's going to happen here, kids? Using Maclaurin is exactly equal to the infinite polynomial of 1 plus 0x to the first over 1 factorial minus 1x squared over 2 factorial plus 0x cubed. What's happening? Can you see what's happening? You got powers to drop out, but who dropped out? The odd powers dropped out, and who stayed, honey? Even, yep, technically right, because this is x to the 0, and 0 is an even number. And what do you know about the graph of cosine? The graph of cosine, OMG, is an even function. What? So cosine is exactly equal to 1x to the 0 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus, if I wanted to keep going, x to the 6th over 6 factorial, yada, yada, yada. The power of being able to write sine and cosine, which are all over the communication field and computers and all that kind of stuff, as polynomials is incredibly powerful. There's a power series, which is an infinite polynomial representation for sine and cosine, which are not polynomials. And think about all the math that we know how to do with polynomials. Whoa. All right. So AP is going to make you construct a series, right? They are. But they are also going to, because that is just a formula, right? They are also going to ask you, they're going to test you on the formula without asking you about asking you to fill in the formula. So this is how. They're going to give you a function, but they're not going to tell you what it is. They're going to tell you it has derivatives of all orders. Orders means there's the first, second, and so on. First order, second order, third order, first order. That reminds me of new Star Wars, right? First order. Anyway, and they're giving me what f is at what? What do you think this number must be? That's the center. They want a third order. That means third derivative was used. There's the check. I got the third derivative. They said Taylor. If they say Taylor, they have to say the center, even if it's 0, even if I interpreted it was 0 from up here. But they want me to use it to approximate a function I don't know what it looks like at point 2, which is close to the center. So they're basically testing to see if you know the factorials, right? Because the polynomial for a function I don't know is exactly equal to the function evaluated at the center, x to the 0, minus the first derivative at the center, x to the first, plus the second derivative at 0, x squared, plus the third derivative evaluated at 0, x cubed. And I've just fallen into a trap. Do you see it? Right? What did I forget? Oh, of course I have to write, if it's exactly equal to, I have to write dot, 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 dot. What did I forget? the factorials. You're not hurt if you forget the factorial here and here, right? Because this is 0 factorial, which is 1. This is 1 factorial, which is 1. But here, you're not going to get the right value if you don't divide, if you don't remember the factorials. So f of 0.2 is approximately the polynomial at 0.2 when I only use these 3 terms. I'm sorry, 4 terms, but third order. Third order. So 3 minus 2 times 0.2 plus 8 divided by 2 factorial is 8 divided by 2, which is 4. Squared. I'm not going to bother to reduce that. I could even just write 3 factorial. And then whatever that number is. I'm going to put it in my calculator because I didn't write it down. 3 minus 2 times 0.2 plus 4 times 0.2 squared plus 4 divided by 6 times 0.2 cubed. And whatever I do, I write 3 places past the decimal. If I typed everything right in, so check my math on this, 871, if I typed everything correctly. All right, AP loves, this is going to show up somewhere, I promise. Okay, important things, they didn't tell me what F was, so I couldn't just look up, right? And have, right, because there are websites where you can say, here's F of X, give me the series for it, right? You can just and type it in and just pops it out for you. So AP loves these kinds of questions because it's not going to help you, right? If you have a calculator program or a computer program, not going to help you. All right, we will do more in our next live session.